So each of the lectures that I record, I try to follow along with the PDF lectures that we've got on the website. Follow them really closely, and I'll try to label them the same thing. So right now, we're going to be doing this lecture right here. And once I'm done, I'll turn off the recording and I'll start a new one for this lecture right here, hopefully, as we progress. And we might even take like a 5-minute break between the two of them. But if you want to follow along, that is where we are. That's what we're going to be doing. And let's see, here we go. So we started on Wednesday. We started this lecture and we got about the first 3 paragraphs before we had to go because we were running out of time. But we were talking about why we would even study chemistry in the first place. And what did we decide about why study chemistry? I see that multiple attendees are typing, so I will stop and wait for you guys to answer my question, just like we're in class. Perfect, to discover how it interfaces with our daily lives, with our daily jobs. That's right. Chemistry was the study of what? Yeah, anything that has mass takes up space. And that's, well, matter. Study of matter, which is everything that takes up space and has mass, which is pretty much everything. So everything that you encounter in your job, everything that you encounter in your daily lives, whether it's something as obviously chemical as a drug or as not obviously chemical as a bicycle tire, that's chemistry. And the technology that goes into discovering the best materials to make the best bicycle tire, that's chemistry, and it's everywhere. So that's why we study it. It's really in everything, literally everything that counts as matter, everything. It's everywhere. But the next question that we have to ask is, how do we know what we're talking about? Because I'm going to talk to you about all sorts of concepts like they're totally true. And you guys, because a good scientist is very skeptical, you guys should ask, how do you know this? How do we know this? You're saying that matter is made up of atoms, but I'll be the first to admit we don't even have a microscope that can look at individual atoms yet. So we've never seen them in particular. How do we know? And the answer to this lies in the scientific method, which you guys have probably heard of many, many times before in other science classes, even in junior high, and maybe before. A scientific method. And the scientific method is not like a checklist that every scientist goes through as they're doing research. So I'm going to give you kind of a list of things in the scientific method, but it's not as neat and tidy as a checklist. You know, and what I say is maybe step 1. It doesn't matter whether this is called step 1, 2, or 3. I'm never going to test you on like what's step 3 of the scientific method. But generally speaking, do you guys remember what are the steps of the scientific method? I don't know, maybe you guys haven't been exposed to this before, but I would be very surprised. Yeah, so the first thing you do is you make some sort of observation. Maybe you run across a certain kind of a problem. State your problem, or you state an initial observation. You think, that's interesting. I wonder why that is. And next, you're going to collect data, which is basically observing more, right? You're not just going to look at one little observation and then jump to conclusions. You're going to say, let's see if I observe the same thing in different situations where it's possible for me to see. Let me ask other people to see if they've observed the same thing, that kind of thing. You're going to collect additional information. And there are two different types of data that we can collect. And I want you to know what these are and what the difference between the two are. So we're going to collect qualitative data and quantitative data. Okay, what's the difference between qualitative and quantitative? Can anybody guess? Anybody that's read the lecture notes? I'm going to pitch in. Good. Qualitative are qualities like color, and quantitative is quantities like amount. Anything that's a number that you could count or measure, my terrible B, counts as quantitative. And anything that's a quality that is not easily expressed by a mathematical number counts as qualitative. You guys with me here? Okay, so those are two types of data that you can collect. Step 3, once we've collected a lot of data, we've made a lot of observations, we want to make sure that we have a strong foundation for what we're looking for. Then we can make a hypothesis. And a hypothesis is just a possible explanation. It's just a guess at what might be happening, and it needs to be tested. It's not really rigorous. It's just based on observation and not testing. And the testing or experimentation is where we really get to know, is this what's actually true or what's not true? So once we make a hypothesis, and a true hypothesis, needs to be testable. If it's not really testable, then it's philosophy rather than hypothesis, if that makes sense. Then the next thing is to design some sort of experiment, some sort of test to see if the hypothesis is true. This might seem like it's a pretty straightforward thing to do, but designing a good experiment can be kind of hard, because if you say, hey, I observed this thing in this environment, I'm going to see if I can observe it in another environment, you might not be actually testing that hypothesis. When you test it, you're looking for ways that it should fail and testing it in those environments. Because then if it doesn't fail, that's what's really exciting and interesting. Does that kind of make sense? You guys are supposed to see a picture of what I'm doing. Criminy. I didn't go back to share my other screen because you guys are still seeing my middle screen, aren't you? Thank you for saying something. There we go. Does that look like something you should be seeing? Yay, there's my whiteboard. Okay, all right, we're all here. Hooray. Okay, yeah, holler if you don't see what I'm doing, because this is basically, it's just like I'm lecturing in the class, where this is my whiteboard, and I'll be writing on it as we have a discussion together, and using different colors like I can on the whiteboard. So you can hear me speaking, you can see the whiteboard, and it should be just like in class, except that you can sit in your pajamas at home. All right, thank you for saying something. This is what you should be seeing as I lecture, yes. All right, so here we go. I started with why study chemistry, and then how do we know? We're going to the scientific method. So design an experiment to test the hypothesis. Specifically, it'll help to test it in a different environment. I mean, you've already observed it in the initial environment, so it wouldn't be helpful to try and observe it more as a test. So look for a different environment. That would be one way to help make sure that it's a good test. And then step 5, generally speaking, based on what you guys typically learn in the classroom, maybe in junior high, is going to be, we're going to repeat the observations we made in this experiment, just get pushed back up to here. So now we have new observations to make that can help us refine our hypothesis. And if we do this many, many, many times in many, many, many situations, then this hypothesis can eventually become a theory. A theory is just a really robust hypothesis that hasn't failed the set of tests yet. Or it could be one that has failed, but it's still pretty useful. So we'll continue to use it in many situations because it's useful enough for predicting what's going to happen. We'll see that a little bit later. But generally speaking, this is how a hypothesis becomes a theory. Now, I made a mistake in my lecture notes. The next paragraph says that eventually you do this enough times with theories, then a theory becomes a law, and that is not the case. Theories and laws are two fundamentally different things. Theories will attempt to explain the why of how something's working, but a law just says this is how something works. It describes a phenomenon. So like the law of gravity was never the theory of gravity. And we can describe the way gravity works mathematically, and it just says this is the way it is, but it doesn't say why it is the way it is. So the theory of space-time might help explain the why of the law of gravity, but theories never become laws. That makes sense. That's a common misconception of the scientific method. I just wanted to point out because I even made it in my own lecture notes. So anyways, this is how the scientific method generally works. And you guys have probably been exposed to it enough to not really be surprised by what I'm saying here. But it's worth underscoring that this is really, 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 really important. There were thousands of years after the initial Greek philosophers that we still had no idea what the nature of matter was because they didn't really look at experimental evidence as being useful. The whole idea was that you should be able to learn everything you could by arguing about a point because then the logic would shine through and whoever had the best argument clearly had the right theory, and whoever won the argument basically got to establish what was truth. And you could do all of this without running an experiment. And in fact, they would kind of look down on running an experiment. That's manual labor. That's for slaves. That's not what we high and mighty Greek philosophers do. We're wealthy aristocrats. We don't do labor. That's a terrible idea. And so they came up with all sorts of good ideas and bad ideas. And in some cases, the bad ideas won out over the good ideas because of the way they were argued. So for instance, the idea of atoms does go back to Democritus and the Greek philosophers. But Aristotle came along and said, no, 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 no. There's no such thing as that. And there's really only 4 elements. And they're, earth and the air and fire and water. And everything is just made of those. And it's really obvious because anything that's solid must be made of primarily earth, and anything that's liquid must be made of primarily water. And the differences between 2 solids just must be minute differences with additions of air and water and fire in different proportions. So it should be obvious that I could take a rock, a lump of lead, and I could just turn it into gold if I could maybe add more fire. It looks like gold has more fire because it's more yellow. Or maybe the difference is that gold has more water because it's softer, right? And so you've got 2,000 years where people were working on the wrong fundamental assumptions because they didn't test it. That didn't seem like it was a good idea. Anyway, so that's my beef with Aristotle. And that's why the scientific method is amazing. Because once we establish that, then all of a sudden, science as we know it and our understanding of the world really took off. And then, 500 years later, we're on the moon. So that's amazing. It's great. So anyways, that's the important thing about the scientific method. But I want to add one thing. there's something in here that's missing from the way that we do science today that is very, very, very important. So I'm going to add it, and I want you guys to know it. Okay, let's see. We'll make it black just because I'm using black. When we talk about repetition, we're going to add publish here. Publish. Okay. Essentially, you collect data, you make a hypothesis, you design an experiment that confirms your hypothesis, or maybe it doesn't confirm your hypothesis. Either way, it's interesting information. And then you put that somewhere for other people to read about and find out about it. And when they read and find out about it, it may be that this applies, that they find it interesting, they want to test it. It may be that this applies to what they do in a way that you hadn't thought about it, so they want to test it in that situation. So when you publish it, you give many other scientists the ability to also repeat what it was that you did. Because it's not enough for me to say, I did this amazing thing and I got this amazing result, so this must be the way the world is. Other scientists have to be able to do the same thing that I did and get the same result that I did in order for this observation and hypothesis to continue. And if they do the same thing I did in a different situation and they get a different result, then maybe this hypothesis needs to be modified somewhat in order for us to all collectively come towards an idea, a better idea of the way the world works. Are you guys with me here? Okay, so this ends up not being repeated by you necessarily, although yes, that happens. But then you have a scientist in Iceland who's like, that's interesting, I'm going to try it out. And a scientist in Texas who's like, this works with what I'm trying to do, I'm going to try it out. And so, and everybody repeats it, everybody goes through the process in testing this hypothesis in different areas of their expertise. And eventually you guys come to a really great idea of the way the world works, and we end up going to the moon. So that's awesome. All right, but the publishing, you have to let people know what it was that you did so that they don't have to repeat all your same work necessarily from scratch. And so that they can also test it. And the publishing is a really important part. You'll probably see this if you haven't done the bad science assignment already. There's at least one case in there where one of the sins, for lack of a better word, of the scientists involved is that they didn't publish their results. They just went straight to the media and said, look at this awesome thing that we discovered. And then the scientific community was like, yeah, that's great. Let's see it. Let's see your publication. And when they finally did come out with it, it was not repeatable. And the scientists, their good name was besmirched. They lost their jobs. And it was a huge scandal. So the publication process, this is how science works. And not a lot of scientists are really impressed when you bypass those results. Maybe go straight to the people and say, look at my miracle drug wonder cure. You should all be taking it. And as a scientist, I would say, yeah, you're scamming people. And I wish I could do that because I'd make a lot more money, but I would feel guilty for the rest of my life. So I don't. But if any of you guys feels like that's something that you'd like to do, I'll tell you, you can make a lot of money on it. For some reason, people don't, if you don't understand this, then it's easy to believe a lot of things that people say, especially in cases where you kind of want to believe it. You guys could probably come up with a couple of good examples of that yourselves. Anyways, that is actually it for this first lecture. There are a couple of good discussion questions at the end of the printed lecture notes. And again, you don't have to post on any of these. They're just ideas. If you find any of them really interesting and you want to talk about them, then you are super welcome to do so. And then there's a reference to the bad science assignment, which kind of goes right along with this. Again, the bad science assignment, you're not going to find any of the answers to this in your textbook. This lecture is just something I feel like you guys need to know as fundamental underpinnings of what science is before we start talking about the nuts and bolts of it. I think you really ought to know how it works. So that's why you've got this assignment. Again, you find all the answers online. And again, I don't care where you get your references, so long as your answers are correct. So I don't need to see like a bibliography. You don't need to tell me where you got this answer. But if you have the wrong answer, you're still going to get it wrong. Okay. This is a little bit of an exercise in how do you find truth? Because I mean, scientists have to do the same thing, right? When we hear about an observation, when we hear about a claim, you know, how do we evaluate whether that's going to be true or not? So that's going to be, I think, interesting and useful because there's a lot of information on the internet, and it's a good exercise for you guys to learn how to find what on the internet is true and what's baloney. So, any questions on this lecture, the bad science assignment? Am I going too fast? Am I going too slow? So long as I can manage to actually share the correct screen, we might be doing all right. Now, I hope you enjoyed that assignment. It kind of sucks me in. I hope it sucks you guys in too. You know, you think you're going to do a 10-minute assignment and then you're like, this is so interesting, and you keep reading because you never heard this interesting story before. Okay, I'm going to stop recording.